Hello and welcome to today's lesson, Linear Regression Confidence Intervals. So our objective for today, by the end of this lesson, I will understand how to construct a confidence interval for linear regression data and why that interval is important to the statistical work that we'll be doing this year. Okay, question of why, first thing we always want to ask. The linear regression lines are commonly used to create prediction models for two variable data. Since these models are not perfect, okay, we know this is one sample, one situation, it's not a perfect line for prediction. We can use a confidence interval to create a range of values that should include the true slope. Okay, so when we're doing linear regression inference, whether it's a confidence interval or a hypothesis test, the one thing that we're looking at is we're really looking at and defining the slope, the rate of change between the two variables that we're looking at in any one scenario. So in our example here, okay, we're looking at golfer scores from the first two rounds of a tournament, okay, and is their first round score a good predictor of their second round score? Okay, so we've got 12 members of a college women's golf team here, okay, and we have their round one, round two scores overall. So now we get our computer generated output of the data. Okay, so we want to remember what this means. And I also have the calculator version of the data as well with this plugged into our TI-84 calculator. So our regression equation, predicting y hat or predicting round two scores equals our y-intercept of 26.33. Okay, so we can see that here as well with the computer printout. Remember, your computer printout, it's always listed in alphabetical order, A and B. Constant coefficient is your y-intercept. Your round one coefficient, remember, round one is x. So that round one coefficient is your slope. So in this situation, the round two score increases by 0.688 strokes for every stroke taken in the round one of a person's golf game. Okay, so for every one stroke increase in round one score, the round two score will increase by 0.688 strokes or hits. Okay, so now if you notice here, we've got a lot of other different information. We've got our R-squared value. Remember, R-squared is the percentage of variation in Y, which is our round two score, that can be accounted for by this least squares regression model of round one versus round two. Okay, we've got our correlation value down here at 0.687. Okay, so that means that it is a moderate positive association between round one and round two if we're looking at it in the linear terms overall. Okay, now in our last unit, we didn't worry about these last values much at all, and this is really where our work's going to be done today. One thing you'll want to know, for almost everything we do, we just eliminate this first column because that's all the information based on the y-intercept, and we're not really looking at the y-intercept here. Our goal is looking at the slope of this line. So now, our assumptions. Can we trust the answer that we get? Okay, assumptions in this case are a little bit different overall. Now, if you notice, we have some of our basics back again. Is it random? Is it independent? And do we have a normal sample distribution? Okay. In this situation, random and independent is both covered by a simple random sample. So you want to say you have a simple random sample. We know it's random. And with a random sample, you're getting independent values of this two variable data. Okay, now, normal sample distribution. We need a graph to show us that we have normally distributed data, and this graph is actually a box and whisker of your residual values. And we want to make sure that the residual values are normally distributed. Okay, so you need to show that graph as a part of your work in verifying assumptions. And then the last thing, and this is new for this situation, is we want to show that we're dealing with linear distributed data. Okay, in order to show that it's linear distributed, okay, we need the original scatter plot, x versus y with our least squares regression line, and then we also need our residual plot to show that there is no pattern in the residuals. Okay, so we would use the no pattern in the residuals to prove that it's linear. Okay, so we work through here. We work with our residuals to create the box and whisker to show that we have a normal distribution. And then we've got our simple random sample that covers both the random portion of our assumptions and the independent, because when you're randomly sampling a data point, you have that covered. Now, if you notice, if we go back to our example, we have 12 members of a college women's golf team, and here are their round 1, round 2 scores. Okay, this is not a random sample. And remember, that doesn't stop our work. You know, that just makes us know and understand that the answer that we get here might not be as valid because we don't know what was happening in this one situation and not dealing with a random sample of situations. So now we look at our calculations. Confidence interval calculation doesn't change. If you've seen any of the other videos, you notice all of these slides are basically the same because you want to understand as soon as you see the word confidence interval, you're going to do the same thing every time. We need our statistic, which is the slope. We need a critical value. Now we're moving back to t. Why are we using a t-value? Because we don't know the standard deviation is unknown, and we're using the standard deviation from the sample as the predictor. Okay, so now our standard deviation of the statistic, okay, S of B1, so it's the standard deviation of the slopes. Okay, you can see a pretty nasty formula overall by hand. If we look at the pieces, okay, this part of the formula is our residual values. Okay, we add them all up, square them, and we divide by n minus 2. And n minus 2 is our degrees of freedom in this situation because we're dealing with two variable data. So we have two unknown values that we can never fill in that have to pick up what's left. Okay, so this is basically the standard deviation of the residuals. And then we divide by the deviation between each x value and x average squared. Okay, so, you know, without having a division by, this is very close to the standard deviation of the x values. Okay, but it's a formula that you're not going to have to use very often, if at all. It's on the formula sheet if you need it. But the good news is this value is given to us in the computer printout. So when we look at our computer printout, we've got A, B, and if you notice, we've got SE of the coefficient. Your S of B1 is right here. Okay, so we actually have that value that we need. So we have almost everything we need in this situation for what we're looking for to build our confidence interval. We've got B plus or minus. We're going to have to find our T star value. Okay, once we have T star, we're going to pull in that S of B1 from the formula so we can start putting in our given values. Our B value, 0.688 plus or minus. T star, we'll pull up the T chart here that's given to you with the test that you just want to have as a resource to pull right from. And then we've got our S of B1 value, 0.23. Okay, now I forgot to pull up the T chart. I'm going to pause here real quick and I'll be right back. Okay, we're back now. I've got the T chart up. I didn't want to waste your time as I pulled that up from the shared drive. Okay, what we want to look at, remember our degrees of freedom is n minus 2. We've got 10 degrees of freedom. I wanted to change things up a little bit. We're going with an 80% confidence interval here. And this is why the T chart is so helpful. It works for any situation. Trying to find your critical T value. We've got our confidence interval levels at the bottom, 80. Okay, we need 10 degrees of freedom on the side. And we just line it up to find our critical value for T for this confidence interval. We're spreading out 1.372 standard deviations in either direction of our value to be able to find this calculation. Okay, so now we've got all the pieces that we need for calculation. Now we need to just run these through the calculator quickly. 0.688 plus 1.372 times our standard error, enter. Okay, so we get an upper boundary of 1.004 for our interval. And then if we want to find the lower boundary, we can go second entry, get back into the formula itself, and then just change that plus to a minus. So we change it to a minus, enter, and we've got our lower boundary of 0.372. Okay, now, why are confidence intervals important? When we look at this range, okay, we don't know if 0.688 is a perfect value, but when we look at this range of values that we're working off of, what we know is no matter what, we have a positive association between round 1 and round 2 scores. Okay, so we don't know how it's associated, but as the round 1 score goes up, the round 2 score goes up with it as well. Okay, conclusion. Same type of conclusions we've had all along. It doesn't change. We really want to get into this consistent model. So we need our confidence level, interval you created, and context of the situation. So wrapping this one up, we are 80% confident that the true slope of the least squares regression line comparing round 1 and round 2 golf scores of these 12 women's collegiate golfers is between 0.372 and 1.004. Okay, now for some extra practice, we've got the in-class packet problems. Okay, this is a really short unit, only 2 lessons here. You want to do everything in the packet except for the significance test questions. Okay, we'll be covering that material in the next lesson. Have a good day.